Okay, let's actually continue our discussion then on state machine design. Now look, more formally, this can actually be referred to as algorithmic state machine design, because look, our starting point is what? Our starting point is really to define an algorithm. And look, it's that algorithm which is really the creative part of the design. This defines really what our system is going to actually do, okay? Now, look, we need to specify whether our signals are really high-acting signals or low-acting signals. All right, now let me just explain a little bit more about that, okay? All right, if a signal is high-acting, it means the action, the activity, if you like, occurs when that signal is a high or a 1. On the other hand, if a signal is low-acting, what that means is the action or the activity occurs when the signal is low. Now look, sometimes, for example, when we draw, if you like, our state box or our state rectangle here, what we put inside this box really represent the outputs. And often what we're just putting inside the box is the outputs that are in fact active. All right, so we might have a situation where we have north, south, green, and we have a situation where we have wait. Now what we're indicating here is that basically we have the north-south green light on and we have the wait light on as far as the crossing is concerned. Now usually what you'd have to do is specify, is this a high-acting signal or is this a low-acting signal? So in a given problem, I would have to tell you that. And I might tell you, for example, look, all these outputs are high acting. In other words, that means when north-south green signal is a 1, the green light is on. Or when the wait signal is a 1, the green light is a 1. So in this case, you'd have to kind of specify, outputs, for example, outputs are high acting, like so. All right, now there is a more formal way to do this, and look, I guess we will be doing both, okay? So sometimes I'll specify outputs are high acting in this manner. If we were doing this perhaps in a more formal way, so we might say or, we might specify like so. We might have our state box again. We have north, south, green, and we might put an H in front of this to indicate that this is a high acting north, south, green. And for example, this might be a high acting wait condition. So really this is a more formal approach. If you use this approach here, it has to be specified somewhere that these outputs are either high acting or low acting. If we were representing low acting signals, so you might have a situation like this. If we were doing it more formally, we might say we've got a low north-south green and a low wait condition. If specified this way, we're simply saying that, look, this is a low-acting signal. In other words, when this signal is a 0, that is what turns on, if you like, the north-south green light, okay? So it's important to understand high-acting signals and low-acting signals, and really to specify that, either in this formal approach or at the side somewhere, we need to specify all the outputs are high acting, or these outputs are high acting, and these outputs are low acting. So that's an important point in specifying clearly your problem. Okay, now look, remember on our state diagram here, I said to you just a moment ago, the rectangular box, inside this rectangular box, we kind of put the outputs, okay? Now these are the outputs, really, that should be active in that given state, all right? The decision diamonds that we talk about, that you've seen before, these decision diamonds, inside of the decision diamonds, these would represent actually inputs to the state machine, okay? So you might have some input, or whatever it is. It could be an input I, for example, and therefore if I is 0, on the next clock edge I might go to some condition over here. On the other hand, if I is 1, on the next clock edge I might go to some condition over here. Now this decision diamond is occupied or is related to being in this given state here. Okay, so this decision diamond here is related to this given state. not the state that we go to. It's related to the state that we happen to be in. Okay? Okay, let's go back to what we had before with our simple traffic light system. Okay, remember this was north, south, green, and wait. All right, this is a crossing system, if you remember from last time. This is a switch. It's a switch that the pedestrian can press to cross the road. If the person hasn't pressed the switch, then we're going to stay in this given state, north, south, green, and wait. If somebody presses the switch, then when the system clock edge comes, we will move to this state and we'll start to change the lights, going from north, south, yellow, and wait. Next clock, we move to north, south, red, and wait. Next clock, we move to north, south, red, and go. And then on the next clock, we come back to the actual beginning again. Remember, we had to have a way of labeling these states. And so we said, okay, they could be state variables A, B. This is the 0, 0 state. This could be the 0, 1 state, 1, 0 state, and the 1, 1 state. Now look, what I want to talk about first of all is really this switch condition over here. Now look at this realistically. Somebody wants to cross the road. What do they typically do? Think about that a second. Yeah, well look, you usually just what? You usually just kind of press the switch, tap it, and you press it momentarily, okay? Expecting that in a given time those lights will change. Now we have to address that because the way we've got it here, if you're pressing the switch, right, the output of the switch, and we have to figure that out, we'll talk about that some more, but the output of the switch will be a 1. If you take your finger off the switch, the output is a 0. So here we have a situation that you could momentarily press this switch and basically the system will not change, the lights will not change. Because really the switch output has to be a 1 by the time you get the next leading edge of our system clock, which will move you into this state over here. So you could miss that. You could press the switch would go high, then low, before ever the clock occurs, and you will not change states. So really this is an issue that we have to try to address. We could actually miss the pressing really of that switch. So look, here is a block diagram of that traffic light system. Remember, this is what we've designed before, the logic that really goes inside here. We've got inputs over here. This is our switch input. This is our present state input here and here. This is our next state output from our state machine. And then we've got our light conditions over here. All right, and I'm just showing the switch coming in like so. Now we've got to sort of look at that switch again, how we're going to build the switch so that we can get logic levels 1 and 0. Okay. But the issue, as I said, is that basically this switch could have been momentarily pressed, and in fact, as a result of that, we may not, in fact, change state. So really we need some way of kind of, as it were, latching or locking in that first press until we, in fact, change states. So let's take a moment and sort of look at a little timing diagram here that might demonstrate what I'm really talking about. Oh, look, here we are. Now what I'm showing you on here is basically our system clock. This is the clock that goes to the state variable flip-flops. I'm showing you the switch condition here, and at the moment we're going to say that it's sitting in a 0 state, okay, or a 0 condition. All right, this is the present state AB values. This is our next state over here, and here are our light conditions. So let's see if we can put some of that information in, all right? So I'm going to say that we're in our present state, all right? Let's represent it perhaps in this fashion like so. All right, we're in the present state. I'm just going to put down the AB values, so kind of a shorthand notation here. I'm going to say A is 0, B is 0. We're in the 0, 0 state. So really, let's look at our next state. Well, since the switch is 0, our next state, well, that really is the same state that we're currently in, which is the 0, 0 state. That's where we sit right now, okay? Then we get the next leading edge of our system clock. Well, the next state we go to, of course, is the 0, 0 state. So we stay in that 0, 0 state, and I'll represent that, if you like, basically like so. So here we are in the 0, 0 state. All right. Now let's imagine during this clock period here, all right, that somebody decides to press the switch, okay, and they just tap the switch. So we'll look at a situation where the switch is just momentarily pressed and we see a logic level going to 1. They take their finger off the button and it goes back down to a 0 again. So what's that going to do for us? Well, let's look at the next state condition. okay, the next state condition. All right, now you could argue that, yeah, look, during this short period of time here, the inputs that we have into our state machine are what? Well, we have a switch 0 and we're in the 0, 0 state, okay? And so we would expect during this period of time here that the next state would still be, as it were, the 0, 0 state. So I'll try to represent that. We're still in the 0, 0 state, okay? Then starting really here, okay, what's happened? The switch has gone to a 1. So we've got a 1, we're in the 0, 0 state. What would our next state be? Well, we would expect now that the next state, yes, we would have moved to what? Yeah, the 0, 1 state. All right, that's what we would expect due to the presence of this being a 1 and in the 0, 0 state. We would expect to move to the 0, 1 state. Let's just go back for a second and look at that state diagram just to clarify that. Yeah, look, here we are. We're in the 0, 0 state. If the switch is 0, our next state, of course, is back to where we were. On the other hand, if the switch were a 1, okay, the next state we want to go to is what? The 0, 1 state. All right, that's if the switch is 1 and we're in the 0, 0 state. The next state that we would go to when we get the system clock would be this state over here. Okay, so let's now go back to our timing diagram once again. All right, look, so what I'm saying then is the switch is a 1, we're in the 0, 0 state, the next state should be this, okay, the 0, 1 state. But look what happens, the switch was only pressed for a short period of time, it is now back to 0 over here. So what does that do? We've now got a 0 for the switch input, and we're in the 0, 0 state. So really that defines our next state as being what? Back to the 0, 0 state. And so by the time you get this clock edge over here, okay, the input to the state variable flip-flops is just 0, 0, and lo and behold, we don't move out of that 0, 0 state. We in fact stay in the 0, 0 state. Okay, and that's because this switch input went back to a 0, defining our next state as being the 0, 0 state. And so when the leading edge of the clock comes along, well, this is what gets loaded into the state variable flip-flops. We stay in the same state. Let's tie that in again with the block diagram. Okay, here's that block diagram again. Now look, remember the system clock, where is that tied? It's tied here and here to the clock inputs of the flip-flops. And these are the state variable flip-flops providing the A, B values. So look, where are we with this? Well, A is a 0, B is a 0, right? Now if S over here is a 0, okay, then we've got 0, 0, 0. Of course, AN and BN would be what? Well, yes, they would be 0, 0. That's fed back, and so when the system clock comes, whatever here gets loaded into the Q outputs of those state variable flip-flops. Okay, so we would not have changed states. So look, if this switch then went to a 1, yeah, sure, now I've got a 1, 0, 0 as an input to, or inputs to this combinational logic here. Sure, that's going to change AN and BN to 0, 1 condition, fed back over to here, all right? But remember, these inputs don't change these outputs until that system clock comes along. So if you had a situation where S went to a 1, but then very quickly went back to a 0 again, what are you back with? 0, 0, 0, which changes this back to 0, 0, which changes, of course, this back to 0, 0. And by the time that clock comes along, the 0, 0 here gets loaded into here, and you have not changed states. So really what you want to do here is when somebody presses that switch, you kind of want to lock it in, okay? Lock it in so that S remains at a 1 until you change states. Now that's an important thing that we have to do to make this a more realistic system. So really what we want to do with this system then is have this switch, yes, perhaps in this period of time here, have this switch go high, okay? And hold it high. Keep it high, really, until what? Until you change states. Okay, so look at this. S is a 1. If S is a 1 here, what does it do to the next state? AN and BN. Okay, well, it's going to change, right? It's going to change this to effectively what? A 0, 1 condition. So this is sitting at a 0, 1 condition. So when this clock comes along, this value gets loaded into the state variable flip-flops, causing us on this leading edge of the clock then to change states where AB becomes 0, 1. But the key is you really have to hold or latch in this switch input condition so that this in fact will work in this manner. So what we do, or what we need to do, is we need to capture, so I'll write this down, we really need to capture really this switch signal, okay? We need to capture that switch signal. And we can use what is called an Sr Latch to do this. Now this is SR, it stands for really set reset latch. Now let me show you a block diagram or a symbol diagram of the Sr Latch. It's got an input S, it's got an input R, and it's got an output which we could call Q. And of course we do have Q bar also available, okay? Let's talk about a little sort of truth table of this guy. All right, so we've got S and we've got R, and we'll talk about one of the outputs which will be Q. All right, so there we go. Now let's look at this. Supposing Q was a 0, and if S is a 0 and R is a 0, we're saying nothing happens, all right? Now, if I raise S to a 1, and let's say Q was already a 0, if I raise S to a 1 and hold the reset R at a 0, the latch sets. In other words, Q becomes a 1, okay? This is a setting function. Q has become a 1. If I now pull S back to 0 and leave R at a 0, the output would stay at a 1. It would not change. Okay, so really this is like somebody over here, activating that switch momentarily, as it were, pressing the switch, right? Press it, goes high, goes low, but we've locked in Q. Q will stay at a 1. All right, now the only way to get rid of that Q is to reset it. So let's hold S at a 0. We'll initiate a reset being 1. This will cause the Q output to go back to a 0 again. And then if I release the reset, 0 for S, 0 for R, we stay, as it were, with the output at a 0. Okay? And the 1 condition will say, look, that we won't do that. So we're going to say that, look, that's not allowed if we want this to operate correctly. So we don't actually apply a 1-1 for S and R if we want this to work properly. Okay? We might in a little bit look at what would happen if they both were 1s. Okay, this will end really part 1. What I want to do in part 2 is really look at what is inside. How would I build one of these Sr Latches?